All right, hello and welcome, guys. Today we are going to we're going to kind of finish up chemical reactions and talk about how chemical reactions go and what are some of the things that we need in terms of energy and how all that works together. So it's kind of the last little bow tie on the end of this unit. So without further ado, let's talk about energy again using those diagrams that we talked about earlier. So if you remember when we talked about endothermic and exothermic reactions, what we were talking about, and we were talking about what was happening with energy, and we had these graphs that look something like this. So on one side you have your reactants, and then on the other side you have your products, right? So going through this, what happens here? And in every single reaction, whether it's endothermic or exothermic, so I'll do both just to show you. And just as a reminder, our endothermic one is going to be the one that absorbed, oops, I just did two of the same. That's not what I meant to do. Our endothermic reaction is the one that absorbs energy, whereas our exothermic is going to release. So this right here would be exo, this right here would be endo. Okay, so I'm going to put my reactants down here at the bottom for my endo, and then my products up here. All right, so every single reaction does require a certain amount of energy in order for this to happen. So every reaction, it's actually going to have a little hill to climb before it goes down. And sometimes, whoa, that looks terrible. Sorry. Sometimes it's going to be really high, other times it's going to be really low. But basically, you need to input a certain amount of something in order for this reaction to go. So it can be something like potential energy that's in those bonds, or it could be something else. So what we're going to talk about is how do we get our reaction to go if we have this kind of hill to climb when we're doing it? And a lot of times, especially in life science and in chemistry and all that stuff, the answer is going to be something called a catalyst. Okay, I'll go more in depth about that in a second. But basically what a catalyst does is it makes that hill that it has to climb, it makes it less steep. We call this right here, we call this energy that we have to put in between all that, we call that the energy of activation. Okay? So the energy of activation is the amount of energy that you need to put into a reaction in order for it to move forward. So sometimes you'll see it abbreviated as like EA or something like that. So what a catalyst does is it lowers the energy of activation. So before we get too much further with our definitions, let me show you a quick demo with how a catalyst works in an experiment. All right, so science experiment, guys. We are gonna do a quick elephant toothpaste thing before, and maybe you've seen it. Here, I'll turn the label here. So you're not distracted. But we're going to try to do this. I haven't done this at home. I've done it a couple times. It's a pretty famous experiment, but it's a good way to show how catalysts actually work. So in here, I just put in some hydrogen peroxide. I'm going to put a little bit more just to show you. Some of it kind of leaked out. There we go. Perfect. Let's get the cat out of the way. Another important science rule for you. Is no cats. Now what I'm gonna add, and also don't try this at home, it makes a big mess and it can also be slightly dangerous as well. So I'm gonna put in some dish soap here. I think that's probably good. A little bit of green food coloring just for funsies. And then I'm going to add in my catalyst. So these are actually all of the reactants that I need for my experiment, but it's not really doing what I want it to, so I'm gonna go ahead and add something to make it kind of just give it a little juice, right? And let's see what happens. And like magic, we're starting to see something, right? Let's see if it gets there. And it is. So this reaction is going to keep going as long as it has enough starting material and enough reactants to kind of keep it going. It's basically making a big foam, and it's going to continue to do that for a while. Now, this actually is an experiment where sometimes, depending on what concentration of hydrogen peroxide that you use, you can see a little bit of steam coming off of it. It is going to release some heat as this happens, so also be careful and all that good stuff. So here is our experiment, and notice what a big difference that our catalyst made in this experiment. So what just happened in that reaction? So the chemical equation for really kind of what happened there is hydrogen peroxide has this chemical formula. And over time, hydrogen peroxide naturally is going to break down into water. And we also get some oxygen out of it as well. So guess what? We get more practice with balancing equations here. So let's go ahead and balance it. We have 2 hydrogens on this side. We got 2 oxygens. And we got 2. And we got, we got 3. So that means I'm going to put a 2 here. And when I do that, I'm going to get a 4. And I'm going to get a 4. So to do, all I have to do here is put a 2 there, and now it's balanced. So this is our balanced chemical reaction. So what's happening when a catalyst is at work is it's speeding this up. The foam, we can see that oxygen escaping further and further. When I added in the yeast is actually acting as our catalyst here. And it also, I mixed it with some warm water, and that caused the reaction to happen quicker and more violently. The same thing will happen if I were to put yeast into a bag with some hydrogen peroxide. Basically, the same thing would happen. You would see the bag start to fill up with oxygen, actually. Instead of just seeing the foam, you would see it start to fill up. The other things I put in are more for effect. So like the food coloring and the dish soap just make it look a little bit cooler. Another way to think about this experiment that we just did is to think about the graph. So you have something like this. We just did an exothermic reaction. So an exothermic reaction would look like this because the reactants would be higher in energy, whereas the products, they would be lower in energy. And that energy gets released to the environment, which you can see as heat. Now, depending on what kind of catalyst I use, you can see the sometimes that smoke kind of come off, and that would be if you use potassium iodine as a catalyst instead of yeast. So something like this. So you have your reactants that are really high in energy, and you have your products that are really low in energy. Now this reaction is going to happen normally, but what I did when I put in the yeast is I basically lowered this so that now I don't have to get all of that energy. I don't have to put all of that energy into my reaction. It happens a little bit quicker and it's easier to see. So again, I lowered my activation energy, right? Cool. So just another example there. Now let's talk about how do we see this? Why does this matter? How do we see this in living organisms? So one of the things that is super important for the human body is going to be the pH. So pH is basically how acidic or how basic something is. And we're not going to go super in depth about acids and bases just for the sake of time. But basically, if your body gets too acidic or too basic in certain places, you can have major problems. In fact, your blood, it's tightly regulated how acidic and how basic it is. In fact, that's the reason why if you try to hold your breath for a really long time, basically your blood starts to accumulate with carbon dioxide, which changes the pH of your blood slightly. You have sensors in a way, like neurons basically, that act as sensors for this pH. And then that's why the longer you hold your breath, the harder it becomes, because your neurons are basically telling you, I need to breathe in because the pH is messed up. So one cool reaction that can happen is something like this. You can take carbon dioxide and water and make something called carbonic acid. Here, let me get the formula right. CO3, there's a 2 there. Cool. So it would be something like this. So that is actually going to be balanced. You don't need coefficients there. Now, it's fairly slow. I mean, I say slow, but it would happen like 0.2 times per second, I think. Whereas if you have a catalyst, if I add a catalyst to it, which the catalyst I would add is something called carbonic anhydrase. Carbonic anhydrase, that enzymes are what we call catalysts when they're inside living things, or it's an example of a catalyst inside living things, I should say. So enzymes are going to be usually catalysts. Basically, they're able to speed up reactions, they're able to facilitate reactions and make them happen quicker. So if I add in this catalyst to this reaction, basically it's going to speed it up so that it is 10,000 to 1 million times per second. So that is a lot quicker. Crazy. In fact, carbonic anhydrase is so important. You find it in the lining of kind of like in your intestinal tract and stomach, and it can create acid. You can also find it in your kidneys, and if it's also in your eyeballs, it helps kind of retain moisture. And if you build up too much fluid, you can end up with glaucoma. So important that you have that there. So that's a good example. Just to wrap this whole thing up, let me give you one more thing about how you can speed up reactions. Okay, so some other ways that we can alter the rate of reaction or how fast a reaction is going is by doing one of these 5 things. So let me change from red. Red feels harsh. I'm not trying to, I don't know, grade something. But anyways, change the volume of the container. So if you change the volume of the container, basically you're creating more pressure in a way, because now those molecules have less space to roam. So if you decrease the space, they're going to react together more quickly. Then you could also increase the amount of reactants. So sometimes we have things that are called limiting factors. So it's kind of like, okay, as soon as I run out of this one ingredient, everything's going to stop reacting. So you want to make sure that you have enough that they're going to keep kind of colliding with each other, keep reacting. You can also increase the temperature. Increasing the temperature is a good way to speed up the reaction because the molecules are moving quicker. They're breaking apart from each other if they have some sort of like crystalline, thing. And we know this from our experiments in class that works. You could break solids apart. That's where if you see that little, it's almost like a little bowl and like a pestle, and you can kind of grind up different things. You can use it in the kitchen, you see these a lot too, for like making guacamole. It's a similar looking tool that you would use in chemistry for breaking solids apart. Because if you have something that's really, really dense, if you have molecules super close together, it's going to be harder for those molecules to react. They're all isolated within each other. So instead, you would start by breaking that apart. I just said that twice. I didn't mean to do that. For 5, what I meant to say was add a catalyst, right? We can add our catalyst and bada boom, bada bing. We're going to have a quicker reaction. All right, guys, that's all I got. Have a good rest of your day. Don't forget to pause, rewatch, take notes, whatever you need to do, and shoot me any questions that you have. Bye, guys.